Hello, we are Team Submarin and our project is the Submarin Drive Assistant. The team members are Lunga Andrea, Katona Ildikó Noémi, Nagy Barnabás, and Popa Katalin. In this presentation, we are going to talk about the problem statement, the challenges we met, our solution for the problem, the results, and optimizations. We will continue with a demo of our application and will end with our conclusions and possible future work.
Often, drivers face different difficulties when driving, like bad weather, bad lighting, or simply being tired. All of this can make the driver less alert. Even though the driver has to be aware of his surroundings at all times, like keeping track of surrounding vehicles and other traffic participants, including pedestrians, he also has to be careful around road signs because a simple mistake could cause an accident and potentially cause property damage or even hurt people. We believe it is important to be able to make critical decisions in such a way that no accidents or collision occur. That is why we have considered creating a driving assistant application.
Some of the challenges we encountered are the following. It was challenging to work with pre-trained models. These models take up a lot of space and a lot of resources to run. We don't really have control over how much time the algorithm will take to detect something. The applications are difficult to be deployed in the cloud because there are little to no free options for dedicated GPU servers. Our application is a mobile application that is user-friendly and has a lot of helping features that could benefit the driver. It offers information about the current speed of the car, weather conditions, and the most important and helpful functionality is to detect other participants, such as pedestrians, car, traffic lights from a photo, taken directly from the application or uploaded from the gallery.
The algorithm we have used is the Tiny YOLO version 3. It's a pre-trained model and we have tested it on two different datasets. On the INRIA dataset, which contains 288 images, and on the Caltech dataset, which is a much larger dataset containing over 10,000, almost 11,000 images. Here we can see the results for the INRIA dataset. The overall accuracy is around 63%, meaning it has detected 383 out of the 589 pedestrians altogether. Also, we have pictured one of the outputs of the algorithm, where it has detected 6 people and 1 motorcycle. Here we can see the results for the Caltech dataset. The accuracy is less than the one we have obtained for the INRIA dataset, which is only 28.71%, or a little over 10,000 people out of 36,000 pedestrians. We would like to note that this dataset is annotated in such a way that it considers a group of people indistinguishable if they are in the distance or if they are in a darker area. It will not label such persons and it will only label the entire group. The reason for the small difference in processing time between the two methods, in spite of the large difference in the number of images, is that the bigger the picture is, the more time it will take for the algorithm to process it. Caltech offers standard resolution images, which are 640 by 480 and which are small, under 100 kilobytes, while INRIA has different pictures of different resolutions, with a size ranging from half megabyte to 2 megabytes, hence the larger processing times. One of the optimizations which we have performed and which has helped our application perform better was resizing the images whose height was larger than 408 pixels. This visibly increased the performance of the application. We have also stored the received images on the server for future use. This can be used to study accuracy but also for statistical purposes. Last but not least, we have also tried switching from the tiny YOLO version 3 algorithm to the full version YOLO version 3, and with this our accuracy increased up to 63%.
We came to the conclusion that YOLO v3 produces better accuracy than Tiny YOLO v3, but Tiny YOLO v3 delivers faster, which means that it is better for delivering real-time results. Our algorithm produces poorer results on darker images. And there is some difficulty of telling apart an individual person in a large group of people. An interesting approach that might benefit our application is to bring the processing of the image and the detection part to the client. This could decrease the processing time and be faster, more close to a real-time experience. Another interesting idea we only laid the ground for is to include different races and ethnicities of the pedestrian detection part. This is the first step toward a more diverse approach in the field of pedestrian detection, and we believe it could be interesting to be analyzed and optimized further.